All right. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, December 30, 2022, the last Earth and Space report of the year. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cloudy but relatively warm winter's evening in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists and communicators, far-flung friends, family, and other curious folk. Thank you for participating. This evening, we are fortunate to have Dr. Lou Mayo, who will talk on the search for life in the solar system. I first got to know Lou some 25 years ago when we were both working at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Even then, he was managing myriad Earth and space research missions along with the data that they produced. He continues this work currently as chief scientist at GAMA-1 Technologies. He also teaches courses in astronomy at Marymount University and serves as president of Ares Scientific. For his talk this evening, Lou notes that there are still a few fundamental questions in physics and astronomy remaining to be answered. Perhaps the most important of these is, are we alone in the universe? Yes or no? Either answer to this question is frightening in its implications. This evening, he will help us explore our own solar system, looking for habitable environments and possibilities for life. Finally, he will briefly touch on results from exoplanet surveys to consider possibilities for life in other solar systems. So Lou, it's great to have you with us. The platform is all yours.
Thank you so much, Bill. It's really nice to see you again and nice to see everyone here. This talk is actually part of a third of a three-part talk on the search for life in the universe, which begins with the search for life on Earth, and then the solar system, and then beyond the solar system. But I thought, given that we have about an hour together today, we'll just confine our question to the solar system. And we're going to be using a few terms, and so I just want to kind of standardize on a few terms. So, for example, when we measure distances in the solar system, we don't generally use feet or inches or meters or even miles, because they run into some big numbers. We often use AU, okay, a much larger yardstick, the average distance between Earth and Sun. It's kind of like a light year. Who knows what a light year is? Anybody know what a light year? Yeah, go ahead. Just unmute and tell me.
I believe it's the distance light travels in 1 year.
Distance light travels in a year. No. A light year is just like a regular year, only it's less filling.
6 trillion miles.
less filling. So it's kind of
I get it now. I'll tell all my friends.
okay, just to get us started. So let's begin with a poll. You all have a button on the bottom of your screen that says reactions, right? You see that button?
Mm-hmm.
Okay.
Yes.
Using a reaction, a raise of hands, how many of you believe that there is life outside of the Earth? Just see a show of hands. You can raise your hand if you want, rather than click the thing. Okay. All right. Get hands down. How many of you think there is not life outside the Earth? Okay. Some. How many of you believe you have been contacted by life outside the Earth? Still two people. Oh, well, I guess those are residual hands there. Okay. That just gives me a sense of who I'm talking to today, what my task is. Okay. So let's begin with what we think of when we think about life in the universe. And I'm going to share my screen here. Let's see, share right here, I think. There we go. All right, so what do we think of when we think of life outside the Earth? Let's see. Do we think of this? Maybe. I remember a talk at Goddard Space Flight Center by a therapist who said he had a whole group of people who believed they had seen and been contacted by creatures like this. Or do we worry about the implications of contacting life outside the Earth? Could be problems, cultural misunderstandings, or this. So we'll be kind of keeping all this in mind as we march kind of through the solar system and look at some big target items, big target celestial objects that we believe have the best chance for life. And we are using your tax dollars very strongly to try to find this. So let's start at the beginning. Here we go. What are the conditions for life? You need to have some fundamental building blocks, right? And the ones that you see in the green block there are what we have on Earth, fundamental building blocks of amino acids and life on Earth. You have to have an energy source, something that gets these things moving, provides some level of energy or heat. It can be chemical energy. It can be sunlight. It can be geothermal, right? And of course, with some of these, such as sunlight, you have the challenge of protecting against cosmic rays or ultraviolet radiation, which can harm living things on Earth. Then you need some chemistry, a liquid to combine it all, to allow these building blocks to come together and form more complex molecules. And if you have all of this, if you have the building blocks, energy, and the water, perhaps you have a habitable world. Doesn't mean you have life, but these are as close as we can come to requirements. Now, as I say this, I will also say that as we look more strongly at the Earth, deeper into the Earth, we find life that exists in very extreme environments. These are called extremophiles. And the more we study and dig deep into the Earth and find the range of environments that life can exist in, the more we expand our reach into the solar system and perhaps the universe, looking for conditions of life outside the Earth. So what do? We follow the water and we follow the biomarkers. And that is the best we know to do presently. So let's take that course of action and see where it leads us. This is an image of Mercury, the planet Mercury. And what you're seeing are craters at its North Pole. And in these craters, some of these craters that have are deep enough and polar enough that the light from the sun never reaches them. We find from orbiting spacecraft like Messenger, we find evidence of water ice, even on Mercury, which can have a surface temperature as high as 800 degrees Fahrenheit, as low as minus 300 degrees Fahrenheit, hot enough to melt lead, colder than dry ice. And at the poles, we still find evidence of water as water ice in these polar craters. Otherwise, it's a hard case to make as a habitable world. Venus gets us a little further along the line. Venus has an atmosphere, an appreciable atmosphere. Mercury does have an atmosphere, but it's very tenuous. Venus's atmosphere is about 100 times the density of Earth's at the surface. It's largely carbon dioxide with sulfur compounds, sulfur acid rains and clouds, not very hospitable to life. And the surface temperature, all day, every day is about 900 degrees Fahrenheit. And that's because Venus's atmosphere is so substantial and so dense that it is very efficient at spreading the heat around the planet. So you don't get much variation in surface temperature. Pretty caustic environment. Now, I'm talking about the surface. This is a thermal profile of how temperature varies in the atmosphere of Venus. So you see temperature in degrees Kelvin. Sorry, I'm switching units on you here. About around 750 degrees Kelvin at the surface. But as you go up in the atmosphere, just like on Earth, in Earth's troposphere, Venus has a troposphere too, and the temperature subsides significantly. So in this region here, and I've noted an identification of phosphine. We'll talk about that in just a minute. But just below what is the turning point of that curve at about 100 kilometers, called the tropopause, you start to get temperatures that are, a lot more hospitable to life. Okay, so the question is, could life exist in the cloud tops of Venus? And somewhat recently, through the James Clerk Maxwell Telescope and the Atacama Large Millimeter Array Telescope, there was an announcement of an identification of phosphine in the atmosphere of Venus. Now, phosphine would be important because it's a biomarker. It is a product of life as we know it. And so this raised a lot of attention and a lot of scrutiny. And I believe currently, I think that there is a fair amount of evidence that this may have been a false identification. It's perhaps an SO2 line or something like that. Nevertheless, this is the kind of thing that we look for. We look for biomarkers in planetary atmospheres as evidence of life beyond the Earth. And as I mentioned, we're going to spend a lot of your tax dollars to do this, at least in the United States, since I don't know where everyone is coming from. And we have 2 missions that have now been approved after years and years and years of no Venus missions. We have Da Vinci, which is, let's see, I think Da Vinci is a Goddard Space Flight Center mission to send an orbiter and a lander to Venus. And we have Veritas, which I believe is the JPL, Jet Propulsion Lab mission, to send an orbiter to look at the atmosphere and surface and map out the surface and look for constituents in the atmosphere to better understand this, what is often called sister planet to Earth. And I'm going to make a case a little bit later on that it's not a very good sister planet, that there are better sister planets out there. So we're marching out from the sun, and at Mercury, we're at about 1/3 of an AU, and at Venus, we're at about roughly 2/3 of an AU. We'll bypass Earth for the moment and go on to Mars, which has a bit of an elliptical orbit, but we'll just say we're at about 1.5 AU, about 1.5 times the distance from the sun as Earth. And so here we have, I believe this is actually a Hubble image of Mars. You can see a number of features here. The reddish areas are dusty areas where it's iron oxide dust has swept over the plains. The darker areas are areas where the dust has been kind of swept off. So you see the ground beneath. You can see evidence of polar caps, which are made of CO2 ice and water ice. And over on the right-hand side, you see there's a little whitening there. That's not an edge effect. That's quite likely water ice clouds on Mars. Now, Mars has a very interesting history. It is very cold. It is very dry. It has lost its magnetic field, which protected it against the solar wind. We'll talk about that in just a minute. And so doesn't appear to be very hospitable to life, but we know that some 3 or 4 billion years ago, Mars may have looked like this, covered in oceans of water, especially in its northern hemisphere, which is lower altitude. Higher surface pressures, warmer temperatures, liquid water flowing in abundance over the surface of the planet and in clouds. So what happened to Mars? We know that from the MAVEN spacecraft that we sent to orbit Mars, that Mars is losing its atmosphere because it lost its magnetic field. Its internal dynamo froze out. And so the magnetic field that protected it from the onslaught of the solar wind, these particles from the sun, it went away. And now the solar wind particles are just knocking its atmosphere off, just like billiard balls. And that has been going on for billions of years. So perhaps there is life on Mars. Perhaps there used to be life on Mars. And we've tried to find it. This is a picture of the Viking spacecraft, one of 2 Viking spacecraft that were sent to Mars in 1976. They had an orbiter and a lander. And these spacecraft, the landers, had a number of experiments on them, including 4 experiments that were meant to find life, if it existed, microbial life, in the soil on Mars. I'll mention 2 of these experiments. One was the gas chromatograph experiment, which, yes, it failed to find evidence of life, but it also failed to find evidence of life in the soil on Earth when it was being tested. So the jury's out for that one. The other is the labeled release experiment. In both of these experiments, there's an arm that dug up dirt, put it in a canister, shut the lid, in this case, added nutrients, and watched to see if there was gas exchange in the canister. And in some cases, there was. So then the question is this life like yeast, right, producing CO2? Or is this purely an abiotic chemical reaction like an Alka-Seltzer tablet? So at that point, they raised the temperature to 160 degrees Fahrenheit to kill whatever microbes might be in there if the gas exchange was caused by life. They ran the experiment again. If they then found no gas exchange, then they said, aha, we found life. Because we had an exchange of gas, then we killed the microbes and we have no exchange. If they continued to find the same results, they'd say, well, it was a non-biological process. And in some cases, they found that there was no longer a gas exchange. Therefore, there was evidence of life, but it was not consistent. It was not consistent. So the jury is out. The principal investigators of these instruments that had the ones that had positive results, even if inconsistent, say they have found life. The scientific community says, well, let's wait and see. So that's where we stand back from 1976. Other evidence. This is a picture of the surface of Mars from the one of the MER rovers. And this is gypsum found in the soil. And we know that on Earth, gypsum is found only in the presence of water. Okay. So this is one strong piece of evidence that water used to flow. Remember, one of our requirements for life, liquid water, used to flow on the surface of Mars. There's other evidence. I'm going to play these three slides back and forth to show you what I'm talking about here. Here's 1, 2, 3, 2, 1, 2, 3. So you see the surface features change, these stripes in the surface changing. There has been some thought that these could be very salty brines of water on the surface. They could also be dust blown on the surface. So I think the jury is out there, but it's an intriguing set of observations. From orbit, we are able, with ground penetrating radar, to identify subsurface aquifers of water on Mars. Again, Mars used to have, very clearly, used to have a lot of water on its surface. Where did the water go? Some of it got broken up in the atmosphere by ultraviolet radiation. The hydrogen left. The oxygen formed probably with CO2, which is the dominant molecule, the dominant constituent of the atmosphere. But some of it slipped down through clathrates in the surface. And so we find these subsurface aquifers of water from orbit. Biomarkers. This is a graphic showing observations of the surface, the Martian surface, and the abundance of methane, CH4 methane, on the surface of Mars. And what we see over a Martian year from spring to winter is that in the colder spring and winter seasons, we don't have very strong evidence of surface methane. And in the warmer seasons of summer and early autumn, we have a greater incidence of observation of methane. This is not evidence of life, but it would be consistent with microbial life below the surface, which would be multiplying and have a higher metabolism during the warm summer months of Mars, and just the opposite for the colder winter seasons. So again, an intriguing finding. We can do this from orbit as well. And we see evidence here, and you can see the legend in parts per billion of methane on Mars as well. So methane is a biomarker. It can be a food for certain life forms. It can also be a byproduct of life. So it's an intriguing finding. Moving on a little bit, I mentioned that Mars lost its magnetic field. We can see, let's see, can you all see my cursor? Bill, can you see my cursor?
Yes.
Okay. Here from MGS magnetometer observations of Mars, the Tharsis region here, and you can see the Valles Marineris, Hellas Basin, and so on. But these colored stripes here are evidence of a magnetic field frozen into the surface. So the surface material aligned, if you will, with a global magnetic field when Mars had one. When the field went away, those magnetic alignments remained, and we can see that in the surface material. This is the MAVEN spacecraft I mentioned we sent to orbit Mars to find out where did the atmosphere go. And it concluded that the primary process for removing the atmosphere was, in fact, erosion by the solar wind. Here we see some famous images. This is the famous Mars meteorite. And magnified, we see this little structure here. Looks a lot like perhaps bacteria on Earth. This was actually announced as we found life. But there are other processes that could form these structures that are not biological in nature. And So once again, I have to report, the jury is still out. Carl Sagan, famous astronomer and astronomy educator, once said, "Incredible claims require incredible evidence." So all of these things that I'm showing you, many of them are highly suggestive of life. But in order for the scientific community to rally behind that and for it to be proof using scientific methods, I'll say, it has to be conclusive, and it has to be repeatable. So, suggestion of life. Here we have the famous face on Mars. This image on the left here was taken by one of the Viking spacecraft in the 70s. Then MGS later, with better technology, 20 years later, in the 90s, took this picture of the face. Here it very clearly looks like a face on Mars. Here it looks more like a mesa. So there are two possibilities here. One is that it's not a face on Mars. It's just a surface feature. The other is that the Martians had 20 years to rub it down, scrub it down for the next mission. We don't know the answer to that, but that's what it looks like from Mars Global Surveyor. And many other pieces of evidence indicating conditions for life on Mars. Here you see what clearly appears to be sedimentary material, the shoreline of an ancient river. And we see lots of this kind of thing, as well as fluvial flow channels like rivers and so on the surface of Mars. Clearly putting it all together, evidence that Mars had a very wet history. So we we send our rovers. I showed you some data from the MERs, Mars Exploration Rovers. This is a Curiosity rover that we sent here. You're seeing it pulverize part of the surface with a laser so that we can see the internal material that is not affected by erosion on the surface. Also a nuclear-powered rover. Curiosity landed in Gale Crater, which is an area that we believed once was filled with water. So those are the kinds of areas that we want to go to if we want to look for evidence of life or past life. And then there's the Perseverance rover, which was targeted for Jezero Crater. Once again, a region of Mars that we believe from clays and sulfates and so forth that say maybe 3 to 4 billion years ago had water on the surface. And here we have a flow channel for water coming into this area, or at least historically. And then, wait, you're not supposed to see that. That's embargoed. I'm so sorry. Okay, let's move on. Let's move on to the outer solar system. We're now out at 5 AU, 5 times the distance from Earth to Sun. And the planet Jupiter has no solid surface. It is a gaseous planet, mostly hydrogen, but it has a number of what we call icy moons. Water ice is ubiquitous in the outer solar system. It's everywhere. And we see this in the moons of Jupiter, Saturn, Uranus, and Neptune, which generally have densities of about 2 grams per cubic centimeter, more or less, which means that they're not made entirely of rock. They have a fair amount of water ice in them. Europa is an interesting prospect. Here we are, Europa, moon of Jupiter. It has an icy surface. We fly our spacecraft by it and look at the change in trajectory. We can identify its density about, again, around something like 2 grams per cubic centimeter. So a lot of water ice. And we also get little tweaks in the magnetometer as we fly by. And what we now believe is that these tweaks are caused by the carrying of current, electrical current, in a saline ocean underneath the ice cap of Europa. And the models suggest that there is more water under the ice caps of Europa than in all the oceans on Earth. So we have liquid water. We have the heat source, which is the tidal friction caused by Jupiter, as Jupiter tugs and pulls on this moon. And it appears that meteoric impacts can break through the surface and perhaps provide amino acids or other organics below the surface, as well as surface, seafloor volcanoes and vents that would provide heat and other compositional elements. So a very interesting prospect for life. And we honor that by sending the Europa Clipper mission. This mission will launch in 2024 and will arrive at Europa in 2030. It is just an orbiter, but it will be able to map out the topography and tell us something about the structure and composition of the surface of Europa. On the drawing boards, but certainly not yet proposed, would be something like this: a submarine to melt through the ice cap and swim below the surface of the ice sheath on Europa to actually look and see if there is life down below. Wouldn't that be something? So we go a little bit further out now. Now we're going out to 10 AU, to my favorite celestial body, Titan, largest moon of Saturn, second largest moon in the solar system, and the only moon with a substantial atmosphere. Surface pressures of Titan are about 1.5 bars, about 50% greater than Earth's atmosphere. And it has an enormous biological soup of chemicals that I'll show you in a minute. This is an image from Voyager 1 spacecraft, which got in very close to get some high resolution images of Titan. Up here, you see a darkening. It's a North Polar Hood region. You can see a change in brightness between the southern part here and the northern part. That is not a solar angle effect. That is a compositional effect from the wholesale migration of atmosphere from one hemisphere to the other on Titan. It's a fascinating place. Here's the Voyager 1 spacecraft. This over here is the scan platform, which could move and target independently of the larger spacecraft. We have imagers, we have UV spectrometer, and we have the IRIS infrared interferometer spectrometer, the infrared spectrometer here that looked for molecular species. This is an image of Titan from Cassini. Notice on the image that we got from Voyager, we do not see the surface. The surface is clouded in this polymeric haze resulting from the breakdown of methane and nitrogen in the atmosphere and the recombination into this incredible molecular zoo. And it really keeps photochemists alive and working on these problems here. But we knew for Cassini that there are wavelengths, 4 primary wavelengths between 1 and 2 microns, where the methane absorption is minimal. And we can then see in the infrared now, not in the visible, in the infrared, in those 4 wavelength bands, we can see to the surface. So here we see Titan's surface, perhaps some cloud activity here. Start to see some structure in the surface here, detached haze layer in the atmosphere around here. It's a fascinating place. This next slide's a little bit out of order, but who cares? This is a future mission called Dragonfly. This is being developed at the Johns Hopkins University Applied Physics Lab. And Dragonfly is due to launch in 2027, arrive at Titan in 2034 for a 3-year mission using a Venus, Earth, Earth, Earth gravity assist. And this is unique because it's a helicopter. It's a drone that will fly around the atmosphere of Titan. Now, I mentioned Titan's atmosphere is fairly thick, so flying around the atmosphere is not that difficult, and it will be able to cover a good bit of ground, sensing both the atmosphere and the surface, and tell us a lot more about what exists underneath that shroud of photochemical haze. So it's a little out of order time-wise, but there it is. Going back to Cassini, this is a picture of Cassini at Saturn with its Huygens probe developed by the European Space Agency. This probe was sent into the atmosphere of Titan, parachuted down, landed on the surface, and we were able to get some very good imaging from this and other data. This is an image from the downward facing camera on the Huygens probe, parachuting down. We see clear evidence of what you might call rivers, or we'll just call fluvial channels here. Liquids on the surface, land features, and likely some cloud features here. These would be not water clouds, but methane clouds. I mentioned that there's a enormous, actually prebiotic chemistry going on in the atmosphere. This is a spectrum from the SATAT link on Voyager 1, taken of the atmosphere of Titan as we scan down from deep space onto the surface of the planet. All of these features here, ethylene, propane, methylacetylene, diacetylene, ethane, hydrogen cyanide, a building block of life. Here we go. Sorry. There we go. Hydrogen cyanide, cyanogen, all these, methane, all these amazing recombinations of methane and nitrogen in the atmosphere. This is the chemistry, the pre-biological chemistry of Titan, which makes it an object of interest when looking for life or evidence of life. Here's the atmosphere, a cartoon of the atmosphere of Titan. Remember Venus as the temperature decreased up to in the troposphere up to a tropopause, just like the Earth. And Titan has a troposphere as well as a tropopause and a stratosphere. We also have evidence of methane clouds, as well as other elements such as hydrogen cyanide and ethane and other molecular species that condense out of the atmosphere at different heights based on the temperature. So this is just kind of a graphic showing this. And then as the stuff condenses out, it forms clouds. And as the particles get larger, the clouds, they rain out and they land on the surface. And we knew this before we sent the Huygens probe to Titan. So the probe was designed to float, to exist in a marshy area or hard terrain, all three. As it turns out, it landed in something of a marshy area. It had a little spring-loaded thing on the bottom. So depending if the spring did not get compressed at all upon landing, we say, okay, it landed in liquid. If it got compressed very quickly and fully, we say it landed on land, and it was something in between. The methane on the surface evaporates, forms clouds again, and rains again on the surface. So we have a methane cycle on Titan as opposed to a water cycle on Earth. Here are some pictures, these two pictures, especially from the lander. Once it landed on the surface, you can see what appear to be rocks on the surface. These are actually water ice frozen like steel. I mean, it's 95 degrees Kelvin, 94, 95 degrees above absolute zero. And so water is frozen out like steel. And it's coated with these what Carl Sagan called tholins, these kind of biotic molecules that are formed in the atmosphere that rain down on the surface. That's why Dragonfly was out of order, because I have two of them. All right, well, we'll skip on this one. Staying out at 10 AU, staying out at Saturn, there is another target of interest, and that is Enceladus. another icy world, another icy moon, with a very interesting property that we saw during the Cassini mission, and that is geysers, cryovolcanism, spewing out from the surface. We were able actually to fly through those geysers, which turn out to be water ice and organics, and collect that material and put it through the onboard mass spectrometer and identify this again as water ice and organics. So another object of interest in the solar system in terms of having the conditions possibly necessary for life, at least under the surface. Let's see how I'm doing. Oh, perfect. One more slide. So where did the water come from? In the inner solar system, it is believed that the planets formed dry, that water could not condense in the inner solar system, at least not with any significance. And so if that is the case, where did the water come from? One strong theory is that it came from small bodies, in other words, comets or asteroids. And the challenge there is to figure out, well, which ones? And the way you do that is you look at the D to H ratio, the deuterium to hydrogen ratio in these objects. Now, it turns out that there are two kinds of water. There's the water that we all know, H2O, and there is also D2O with 2 atoms of deuterium, which is a hydrogen atom with an extra neutron. And these exist in a ratio of about 1.5 times 10 to the minus 4th, or well, depending upon which way you do it. There's about 10,000 times more H2O in our oceans than D2O. So we have that ratio. And when we go looking for sources of water for the Earth, we want to find that D to H ratio. Which objects in the solar system might be responsible for depositing water on Earth that has the same ratio of deuterated water to H2O? Most comets do not. I believe there have been a couple who do. However, it appears that asteroids may have that ratio. So it could be, in fact, that asteroids brought much of the water that we now have to Earth in the early formation of the solar system. And in addition, I think, to outgassing by the planet. So I will end my talk there and open the floor for questions. I'll stop sharing.
Okay, everybody's back. That's great. Feel free to unmute. And
I have a really quick question. Get it out of the way real quick, if that's all right.
Sure.
Your slide on Enceladus. What took the picture and what's in the picture?
Oh, it's not a fair picture. Let me go back.
Okay. Thank
Hold on. I'm going to answer your question.
it looked like a guitar.
It did, didn't it?
It looked like
That was
a
that was the
satellite to me.
spaceship. That was Cassini.
Hold on. Let's see, I need to click there. There we go. Okay.
That's Cassini.
Obviously, the spacecraft here is input. Okay, photoshopped in. But the image here is from Cassini, from the Cassini imager.
Well, I knew it couldn't have been the other Voyager because I took a left turn.
Yeah.
Titan.
Weren't at the same time either.
Voyager 1 did. The rest of its mission was sacrificed in order to get up very close and personal to Titan. And of course, Voyager 2 went on to Uranus and Neptune, and they're both now out beyond the heliopause in interstellar space. Does that answer your question?
Thank you.
I got a question, Lou.
Yes, sir.
You're showing on Venus that we're sending an orbiter and a lander. Now, we already know that the Russians put a couple of landers down They didn't last very long. How come they didn't have a balloon or something that would stay in the upper atmosphere and hover, or at least go up and down and not try to get too low and get crushed?
What a great idea. I can't tell you why the Russians didn't do that, but
How come we
yeah,
don't do it?
a balloon floating around in the zonal winds of Venus could be very informative.
I mean, if they
I
can get
agree.
something to fly on Mars with almost no atmosphere, they could certainly get something to fly in Venus at a higher level.
Mhm. Yeah, I think it's been thought of, but there are no missions on approved to do that presently. It's a good idea.
I'll join you guys.
Come on down.
It'd be wonderful.
Yeah, I have a question and a comment too. First, my comment is, you have a responsibility to the public, and you should tell them the truth about the Looney Tunes making it to Mars. The people have a right to know. So, just wanted to.
Martin the Martian.
Oh,
Yeah,
I thought
exactly.
I'm hoping that the audience that I'm talking to would have gotten that, but yes,
Yeah.
that was a little joke.
We're
There
gullible.
are no
Oh, it was a joke.
cartoon
Okay.
characters on Mars that we know of.
Right. Yeah, my question though is, now people keep saying this, and I've been told that it's not necessarily true. They keep saying that, oh, Earth's magnetic field has protected its atmosphere, and Mars doesn't have a large scale magnetic field, so that's why it was stripped off. But I've been at one of these Zoom sessions with Earth scientists, and they're saying it's the opposite, that the magnetic field allows the sun to strip off the atmosphere more quickly. So I'm not sure what to believe. I just wanted to point that out if you're unaware of that apparently
I
that's
am certainly not aware of that.
yeah, there's plasma physics involved there, so it could be a
That's
little more
right.
complicated.
That's right. This
Yeah.
is heliophysics.
Yeah.
I don't think that's correct.
Yeah, well, that's what the Earth scientists
There-
seem to think.
There are places in the Earth's magnetic field that will allow solar wind to penetrate, but overall, it rebuffs. In other words, these particles from the sun, many of them are charged particles, and as they move, as we know from Michael Faraday in the 1800s, you move charge and you generate a magnetic field. So these particles are carrying part of the sun's magnetic field with them. And
Right.
they actually bump into the Earth's magnetic field. And we know that the field is protecting because we can measure the degree of deflection. In other words, the pressure and the pushback from the Earth's magnetic field with magnetometers around the planet. And these magnetometers produce a composite data set called the KP index that tells us how strong the magnetic field impinging on the Earth's magnetic from the sun impinging on the Earth's magnetic field is. So I have never heard that before, and I would invite you to explore that a little further, and I'd certainly be interested in what you find out.
Yeah, that would be an interesting thing to find out. So yeah, thanks.
We have a question from Phil and Susan Schwartz as to what caused Mars's magnetic field to collapse.
Right, that's the right question to ask. It may be a few things. Mars is smaller; it's about half the diameter of the Earth, much smaller, and so it may be that the Mars internal heat source of its core eventually lost enough heat that the flow of metals around the outer core froze out. What would have facilitated that? Well, Earth's core is largely heated by radioactive decay. Perhaps there was less radioactive decay, radioactive material in the core of Mars. But some combination of those two, I think, would be the answer.
So is this being taped?
I'm sorry?
Yes. It is taped.
Yeah, it's being recorded. This is being recorded.
Yes.
You didn't talk about Pluto at all.
I didn't. But thank you, sir, for, yeah, Pluto sure looks like a planet to me, especially after the New Horizons flyby and its moons and its dynamic surface, its atmosphere, and so on. The issue is that we're finding with better telescopes and better detectors, more and more objects out beyond Neptune, trans-Neptunian objects that are, roughly the size of Pluto. So we had to make a decision. Do we invite all of those in as planets? Now we have 13, 14, 15, who knows, planets. Or do we cut it off? And the International Astronomical Union, which is responsible for naming celestial objects, formed a committee and decided that there were 3 criteria for being a planet. The first is it's got to orbit the sun. So Ganymede and Titan are both larger than Mercury, right? But because they orbit planets, they are not planet candidates. It has to be large enough to be round. So you get enough mass together and it pulls in, right? The gravity from the mass crunches things in the same on all sides, just like you have a snowball that you're making, right? If there's not enough of that material, then there's not a lot of force to create a round object. So it's got to be big enough to be round. Pluto does fine with those 2 criteria. The third criteria, which is, has been challenged, but is the one that Pluto does not meet, and that is to be an efficient vacuum cleaner sweeping out the debris in its orbit. And Pluto does not do that efficiently, and so it did not make planet status.
I was thinking more along the lines of the Folans and the chemistry of it rather than, it's like Titan, where you got something going on there with the heating and the chemistry of water and the other ices that look like it might be, something going on biological.
Well, that that was not considered in the IAU committee, apparently.
That committee seems to have done away with exoplanets as a category.
Now they're dwarf planets.
No. There can't be an exoplanet if it doesn't orbit the sun.
Oh, well, that kind of ruined it.
Well, exoplanets are a category. We present them at the Division for Planetary Science conferences. We present them at the American Astronomical Society conferences. It is a frequently used term. There's an exoplanet archive that NASA maintains.
Well, no, of course, please don't take my my remarks seriously. I was asking if they might have fixed the language from so it's not orbit the sun, but orbit a star or something like that.
Orbit another star.
I see.
Well, possibly, yeah.
Our sun or a sun.
Or a sun, yeah.
I'd like to get back to Titan, which seems to be your favorite. And if you could comment on the fact that it's wicked cold at Titan. And so, yes, you might have some organic chemistry taking place, but it must be taking place wicked slowly.
Or below the surface.
Oh, yeah.
Where
Below the
there's
surface.
some
Titan
sort
does
of
have a
heat source?
3% eccentricity. I think it's 3% in its orbit. Its orbit is slightly eccentric. And we also know, again, flying spacecraft by Titan, watching their orbit deflect, we know what its bulk density is. Like I said, roughly 2 grams per cubic centimeter. So there's a lot of water ice. And some models suggest that there may be liquid water below the surface.
Is it radioactivity or other form of internal heat, or is it all tidal? The energy that
Yeah, that I don't know. I don't think we don't have any strong evidence of radioactivity internal to Titan. So I would say what we think we know is that it's tidally generated.
Now, in Clark's 2010, Sorry, go ahead.
I don't mean to interrupt. I just want to try and get my question in.
Sure.
Can I ask a question about exoplanets? It seems to me that when I've seen discussions about exoplanets, one of the criteria about looking for life is that it has to be within the Goldilocks zone.
Mm,
And everything that you seem to be partial to in the looking for life in our solar system is way outside of the Goldilocks zone. So is that not an important criteria anymore, or do we just leave that alone?
well, that's an excellent question. As we look at the Earth and we look deeper and deeper and find these extremophiles, and we find life that exists just fine in very harsh environments.
Yeah.
The Goldilocks zone kind of takes on less and less of an important meaning. What the Goldilocks zone gives you is liquid water on the surface.
Right.
Okay.
It's like our own planet. It's looking into our
Right.
own.
That's right.
Mhm.
Now, there are other factors, not just distance from the star, but the atmosphere that can have a greenhouse effect on surface temperatures, as our atmosphere does, as Titan does, as Mars does, certainly Venus.
Yeah.
But generally speaking, it is the distance from the star that allows liquid water to exist on the surface. Now, if you want to talk about life underneath the surface, as we're doing with Titan and Enceladus and Europa and so on, then, I guess you don't need to be in the Goldilocks zone.
Yeah, okay.
That's a good point. Well, I teach at Marymount University, and I have a lot of international students. So I talked to them about the Goldilocks zone, and I found out very early, years ago, that all the international students get that wrong on the test. They don't know the story of the three bears. So I have to talk about the habitable zone,
Yeah, right.
anyhow.
Thank
Yeah,
you.
I wanted to ask you about the ice moons, like Europa or Enceladus. I remember reading that they can have cracks on their surface, and within those cracks, you can have liquid water. So they talk about having, drilling into the ice to sample the liquid water, but maybe they don't have to do that. If you go into these cracks, apparently there is some liquid water there because it's so much salt dissolved in it that it stays in liquid form for a long time.
I'm not sure about that. When you get out at 5 and 10 AU, you're talking about extremely cold temperatures. Even on Mars, there's some question as to whether or not you can have with the cold surface temperatures on Mars, whether you can have water that is filled with enough minerals or salts to exist on the surface. So I'll just have to say I'm not aware what physics is, but we know, for example, on Triton, not Titan, but Triton, we have sublimation of ices on the surface that create these cryovolcanoes. But I'm not aware of I'm not aware of liquid water on the surface of any of the outer icy moons.
But with Jupiter's tidal kneading of Europa, it was kind of keeping the heat level where you got a 60-mile deep ocean under a crust, and you do have stuff that's spouting up through the surface that you could fly through.
Oh, you're
Getting
mixing your
confused.
moons. Europa does have a liquid ocean underneath, but we don't see the water ice geysers on Europa. We see those on Enceladus.
Thank you.
I have a question. In these very, very cold environments way outside the Goldilocks zone, is there any basis for considering that there might be life which forms around silicon chains rather than carbon chains at very low energy, very slow moving, very cold, sort of, 78 RPM record playing at 16 RPM,
Well, thank you for your advocacy of Star Trek, sir. Much appreciated.
Oh, really? Was there a Star Trek episode?
Yes, it was with a Horta. Yes, sir.
That
Ah.
posited silicon-based life. Wow.
Yeah.
Yeah, this has been proposed. Silicon is a possibility.
It's the
Um,
next row down with the same.
it is more abundant than carbon, so it's got that going for it. But its outer electron shell requires 18 electrons, and for carbon only 8. So the bonds that it makes with other elements are more feeble. In addition, I mean, we began all this by saying liquid water is necessary because that's what we find on Earth. So in the presence of liquid water, silicon compounds tend to dissolve and react with hydrogen. And it just makes the bonds, very weak. So, I don't know. The answer is I don't know, but I can tell you that carbon is a better candidate.
Right. Just structurally and yeah.
Silicon certainly makes rock very well.
Yes. And I like William Wall's comments in the chat that silicon-based life runs the internet.
You bet.
That may be where we're headed in 100 years or so.
Quantum computing.
GPT chat becoming the predominant life form on the planet, right?
David Kurt has a long question having to do with Earth's changing magnetic field, both in direction and in strength. And so perhaps you don't need to comment on that fact of Earth or that finding of Earth, but how changes in planetary magnetic fields might be of interest.
Well, we've talked about Mars. On Earth, we know that the Earth's magnetic field flips every some tens of thousands of years. I forget what the number is. And we look back in the geological records, and we don't see any evidence of mass extinctions as correlated with those changes in magnetic field direction. So I imagine, GPS might have a problem. Maybe birds have a problem for a while, but we don't see any evidence of any strong mass extinctions as a result. So that's what we know.
Well, are there any other questions? We're getting close to the end of our time. Any other questions people have?
I
Well,
like your mobile on the ceiling, Louis.
Yes, that's a very high resolution. Here we go. Image of this model of the solar system.
Ah, yes.
Takes hours of computing power to generate that.
A Calder enthusiast.
Yeah, I love Calder.
Yeah. I got the same curtains on your window in my living room with the big loops.
Oh, you're the guy who took my.
Yeah, I took the other ones. Hey, thank you very much. It's a great lecture.
You're welcome.
I have a question.
Dave,
Yeah. So Jupiter, the atmosphere of Jupiter, the last I heard, actually the last several times I heard tuned into that, there's a lot going on with perhaps organic matter in the atmosphere of Jupiter, and it's a very thick, dense atmosphere. Do you think that we'll find life there?
You know what's interesting about your question? I wonder if I can find this. Give me just a second here.
I thought that was mostly hydrogen.
Just a second. Here we go. Here we go. Okay. When I was growing up, I was very interested in astronomy. A lot of astronomers get interested in elementary school or before. And my aunt and uncle would send me this book, a book like this from the Time Life series of books. This is back in 1963, I think, or something like that.
Yeah.
So what do we know? What do we know about the solar system back then? Well, there's a picture in here somewhere that I think that answers. Maybe I'm remembering wrong. Let's see. Well, maybe I won't find it.
Picture of organisms floating.
Big jellyfish
Yeah,
floating,
it's a picture of these big
gas
kind of
bags.
balloon creatures
Yeah.
floating in the atmosphere of Jupiter.
Mhm.
So is it possible? Who knows? I don't know how to answer a question like that. Is it possible? It appears that life began fairly quickly. Once the Earth had settled from formation.
Mhm.
Which suggests to me that, I just say suggests to me that life wants to exist. Anyone who's ever watched a weed grow out of a crack in a sidewalk,
Mhm.
right? Can attest to that. Is Earth the only place where that would happen? Well, I don't think so. Physics is the same. 400 years ago, we didn't know this, but now we know the physics of the rest of the universe is the same as the physics down here with the unwashed masses on Earth. Yes, when you find organics and you have a heat source and you have some fluid that can mix them together, yeah, I think it's possible. But it's hard to answer questions like, could it ever be?
Well, that is a great way to close this session. I thank you, Lou, and look forward to lots more interactions. It's been way too many years. And I want to thank my fellow water bags. Terrible way to say it, but life forms over Earth's surface. We have a pretty good representation. And I want to wish Dick, Lukey especially, that he gets better and better, just because he had to deal with it. It's not even a life form, but something which was potent. So I thank you, Lou, and thank you all.
Happy
Take
New
good
Year
care.
to everybody.
Happy New Year, everyone.
Thank you very much. Excellent.
Okay.